In our previous lab, we have studied about FIR filter designing with uh, window and without window. We see that very elaborately and implement the Python coding in the previous labs, right? So in this lab, we are going to see about how to write the Python code for infinite impulse response filter, that is IIR filter. Uh, so we are going to actually design the IIR filter here. In theory classes, you people have studied about this IIR filter. So you people know about the basic thing, that is basic theory that is behind the IIR filter. So still, I'm going to give a little idea, or you may say uh, something about IIR filter. So in IIR filter, as the name suggests, it's a infinite impulse response. Okay, but in case of the FIR, that is a finite impulse response filter. Uh, First thing, and the second thing is that in FIR filter there is no feedback path. Okay, so but in case of IIR filter, we have a feedback path. Okay, so in relation of different filters, FIR filter, you may see that it is little bit unidirectional. It is not coming from any in that relation the uh, graph flow, or you may say the flow, or I am actually forgetting the actual term, that graph, signal flow graph. Yeah, signal flow graph. If you see that, then it will not coming any uh, thing. It's not coming from feedback. It is only uh, from input to output side. But in case of IIR filter, we have a feedback path. Okay, so for getting some basics idea about IIR filter, I just search on Google. So let me show that. Okay, so I already told about what is the IIR filter, what is IIR means. So then next is the why the impulse response is infinite. Okay, the impulse response is infinite because there is a feedback. This also I told you, right? So then, what are the advantages of IR filter as compared to FIR filter? It's an important point. You should know that, right? So IR filter can achieve given filtering characteristics using less memory and calculation than the similar FIR filter. This is the main advantage we are actually getting uh, from IR filter over FIR filter. Okay, because in complex computation, we may need we have to, or you can say like that, the signal that um, we have to process is very large, right? So if we implement that signal with a lot of number of FIR filter, it will take a huge memory as compared to IR filter. The same data can be processed with IR filter with less memory. Okay, and if we use their FIR filter, it will take a high, or you may say a large amount of memory there. Okay, so these are some basics thing about the FIR filter, sorry, IR filter. Now we are going to see what we are actually going to uh, see in this lab. Okay, so what I did is the FIR filter designing is we can design FIR filter with different methods, like we can design Butterworth filter, then Chebyshev type 1, Chebyshev type 2, then we have elliptic, then Bessel's. There are many type of uh, there are many ways in which we can design a uh, FIR filter, or in theory classes also sir has told about. I want to correct myself that the IR filter designing methods are four types, right? That is impulse invariant method, bilinear transform method, then frequency transformation method, then approximation of derivatives method. In theory classes, Sir has elaborated these things, so I'm not going into depth into that. What my point is that uh, I'm going to use here only bilinear transformation method. Okay, the rest of the method I'm not going to use it here because Python provides bilinear transformation method. So for other method, I actually don't know. So maybe there are some module or some packages where we can use other method for designing IR filter. I actually don't know that thing, but I the all the program that I'm going to write in IR filter designing is I am going to follow the BLT method, that is bilinear transformation method. Okay, then next thing that is that I have told just earlier that about Butterworth, Chebyshev type 1, type 2. Okay, uh, these are the type of IR filter, right? So we are going to see for Butterworth and Chebyshev filter. But in this lab, I am going to uh, tell you about the designing of Butterworth IR filter. Okay, so I think it is pretty much clear to all of you what actually we are going to do in this lab. And in the next lab, we are going to deal with Chebyshev type 1 and Chebyshev type 2. So in this, we are going to design the filter. Means what? We are going to design low pass, high pass, and band pass and band reject filter, right? So uh, So the IR filter can be designed in two ways. One is in uh, digital domain and one is in analog domain. Okay. So in theory classes, Sir has told you about how actually the analog get converted into digital domain and other thing we people have already studied about that thing, right? So here my main what I am going to do here is I am going to do the both type of filter design. Okay, one is for analog Butterworth filter and digital Butterworth filter. So for every okay, I'm going to tell that what the design criteria. So before that, let me tell you that here we are going to use different libraries. So what I'm going to do here in today's lab is that I'm first going to write a code first. Okay, then I will explain one by one what library that the library that I have been used in the writing the code. Okay, so it will be better because if I explain you from the beginning, then you will just mess up because it will little bit different. I am going to uh, approach in a different way to this lab because the plotting part I'm going to little bit modify. I just modified some uh, part, so I'm going to do it in a different way today. It is a little bit uh, means tricky, you may say, right? So please listen carefully and uh, do your lab. Okay, so before going into the first coding, let me list out the thing that we have to do in this lab. So we are going to design of IIR, or you may say infinite impulse response, or I'm giving IIR, right? IIR filter using, I'm mentioning here, bilinear transformation method, or you may say BLT, right? So I'm going to design this IR filter. Okay, so what I'm going to do in this class is, first designing of Butterworth filter, that is low pass, high pass, then band pass, then band stop, right? These four type of filter we are going to implement. Okay, next thing, let me give you the design criteria here, what the design criteria is. Okay, so to list out the design criteria are, first, order of the filter. Order is equal to, I am going to take as 3. Okay, then the cutoff frequency, or you may say FC, I am going to take it as 1 kilohertz. uh, this data actually I am taking from your theory class. First, maybe the first problem, I don't know exactly the problem number, but it is from the theory class, right? Theory class. So let me, order of the filter is, sir is taking 2, I am taking here 3. That's the only difference. Then cutoff frequency is 1 kilohertz. Then sampling frequency I am taking as, so let me write sampling frequency, that is nothing but Fs. This is equal to, I'm taking as 10 to the power 4 sample per second, or you may call that is 10 to the power 4, or 10k, 10 kilohertz. Okay, so all the data, that design criteria I have taken from your one of your theory problem. I only changed the order of the filter here, that is 3. Okay, in class it is given 2. So these are the thing that we are going to do today. And okay, so this is for the high pass and low pass. So for band pass, let me make a comment here for band pass and band stop. Out of frequency, that is FC, I'm going to take it as 100, or you can take 500, 1000. Okay, okay, it will be better. So these are the for band pass and band stop. We are going to take two frequencies, two cutoff frequency for the band of frequency to pass through it. So for that, I am going to take this parameter. So now let's start our coding. Okay, so what I'll do is that I will write a in a single cell both for the analog Butterworth filter and digital Butterworth filter. So let me make a comment here, that is Butterworth low pass filter. Okay, so let me make this as a heading. Okay, so now we are going to take the library first that we actually need. Then so first thing, that is from numpy import pi comma block 10. Okay, then next library from scipy dot signal import better, then fix then sos fix. Okay, so yeah, this much only. Now let's for the okay, don't uh, panic about this thing. This thing I will elaborate in a precise manner such that you will get the thing. Okay, so let me write the code first, then I will be uh, take every point individually, and I will make you clear, make the clear, make all your doubt clear, right? So from pylab import okay, then import plot the dot py plot as plt. Okay, okay, so yeah, this is the thing that we actually need. Okay, now let's run it. So in this cell we are going to write the code code for the for designing the IIR analog and digital IIR analog and digital Butterworth low pass filter. Okay, so we are going to now we have to write the code. So let me start with the first thing, that is P comma A is equal to butter P comma that is 1000. Okay, then the B type is equal to low pass. Okay, then analog is equal to true. Okay, so it's about H is equal to fix comma then taking 1000 or you may take 0 to 4. So yeah. Then H dB is equal to 20 log 10 log 10 H. Okay, next, yeah, we have done the mental designing, but now we have to plot the characteristics. we, this is the plotting section. Okay, so okay, the comment that I am going to give after my uh, after the understanding. Okay, I am going to take every bit and I'm going to uh, elaborate that thing. So at that time I will going to comment on each and every line what I am going actually doing by writing this code, such that you will get a clear idea. So let me start the plotting. And from the starting I already told you that here I am taking a different approach to plot a graph. uh, that previous one that I have showed you can do with that also. But uh, for give you some extra information, I just did I just select this approach so that you will get a new idea how to to plot a graph in Python. Okay, so let me start the plotting section here. To go is equal to what is the directly we can write figure. Okay, then right, fg is equal to fig1 dot add subplot 1 comma 1 comma 1. Okay, then fg dot semilog semilog x bracket equal to w comma h hdb. Okay, then dot set title as Butterworth IIR analog low pass filter, or you can write like this also: frequency response of Butterworth IIR analog low pass filter. Frequency response of Butterworth IIR analog low pass filter. Yes. Then for the giving it to level, so fg dot set slash x level is my frequency in hertz. Okay, frequency in hertz. Then here we are going to plot the amplitude in dB, right? So let me make it clear. Okay, Then next thing, fc dot grid is equal to both, and x is also both. Okay, then g dot t dot so. Okay, this is for we finished for the analog Butterworth filter. Let me make a heading, make a comment here, that is for analog LPF. Okay, yeah, LPF. Now let's write for the digital IIR low pass filter. Okay, for the digital IIR low pass filter. So what's the changes that we are going to do here is, as the name suggests that it's a digital filter, here we need sampling frequency, right? This is the basic thing. You people all you have know this thing, right? So for that reason, I already mentioned that the sampling frequency that I'm going to take is 10 kilohertz. Okay, so with that parameter, I'm going to design the filter here. So let me first define the sampling frequency, because in digital filter we need that, right? So 10 to the power 4, yeah. Okay, then here I am declaring a variable that's called SOS. Okay, I am going to tell you what is this SOS, and for why I am taking this variable name as SOS. You can take any name, okay, but for the simplicity sake, I just take this name as SOS such that I can explain the thing to you. This is only a variable name, okay, don't confused. Later on in the SOS term, one parameter also come, that time I will explain the thing. Okay, so send butter 3, yeah, then the cutoff is 1000, right? So 1000 divided by fs, because I am designing a digital filter, I have to divide it. Okay, we already seen in uh, FR filter designing also. B type is equal to low pass. Okay, then the next thing is analog. Here we have to make it false because we need false a digital filter, right? So the next thing that is I'm going to take here is output. It's capital. Output is equal to SOS. Okay, second order section. It's full form. SOS full form is second order system or section, you can say. Second order section. I will tell you while we are going when we are going to see about the butter what the this parameter are stand for. In that type I will tell you about SOS, and I will clear your doubt at that time. Okay, so next thing is which is equal to SOS user freaks SOS 2024. Okay, then now let's move to the next thing, that is the conversion of HDB. Sorry, it's equal to, we know, 20 into log 10 in bracket, put absolute value of H. Okay, then we are going to the next section, that is the plotting. Let me separate this plotting part. Okay, is that okay? So first, that is figure 2, which is equal to plt dot, or you may figure 2 right directly. I can write, yeah. Then just clf function. Then next one is z, which is equal to t2 dot add subplot bracket 1 comma 1 comma 1. Okay, next that similar to, it's pretty similar after that, fz dot set title. For that, frequency response of Butterworth IIR digital LPF. Okay, so frequency response of Butterworth IIR digital low pass filter. Okay, then fz dot set x level. Here in x level, it's normalized digital frequency. Oh, one thing we forgot to do, that we have to plot it first, right? Then we can. I didn't plot it till now, so I have to plot the first. Then I can set the arguments, right? So exit dot plot divided by pi, or you may call max of w also, because it will give pi only. In digital domain, the maximum frequency that we are getting there is pi, right? So, okay, for better understanding, let me write max pi. Max of w, it will be better because in previous lab we have used like this, right? So next thing is that HDB, yeah, this much. Then let's finish. Let's go to the next line, that is LT dot y level. In y we have amplitude in dB. Okay, in dB, right? So let me make it similar. Okay, yeah. Now we have to, yeah, what I did here, LB. What is LB? No, it's good. Then fg dot grid, which is equal to both. Then axis is equal to both. Then plt dot show. Yeah. Okay. I think this is all about the coding. So let me check it once again, because I make mistake many times. So let me see it once. Okay. I think it is okay. Now let me run this code, whether it is giving us output or not. Then we are going to see each and every line of the code, and I will tell you what's the theory behind that. Okay, so let me run this. Yeah, we have got some error. Maybe it is small, right? So yeah, okay, now it is set. Okay, we got the thing. Now it is working. Yeah. Okay. So okay. So now let me tell you, or let me decode the code for you, right? I am nothing but I'm going to decode this code such that you can understand, right? So for that, the first thing that is I'm going to explain here is, this is butter, right? And this butter command, or you may say uh, module. I am exporting this module from scipy.signal, right? So what I did here is, let me search scipy.signal.butter. So I'll get this thing. Let me go that. Yeah, you can see here it is a Butterworth digital and analog filter design, right? So what are the parameters here? First is n. This is the order of the filter. So what is the order of the filter here? My 3, right? I already told you from the start uh, start of our class, right? Then omega n, it is the critical frequency. Okay, or frequencies means in case of band pass or band reject, we are going to give their range of frequency, right? But here it is a, as it is a low pass filter, we have only specify a single frequency over here, right? So this is the critical frequency. And what is the critical frequency for us? 10 to the power, or you may call 1 kilohertz, right? The next B type, low for low pass, or you may write directly low pass. Okay, the by default is a low pass. Okay, be careful if you are not mentioning the B type, then it will by default it will take it as a low pass. Okay, then analog, true or false. What is analog? When it is true, we retain an analog filter, otherwise it in a digital filter. Okay, so here in the first I make it true, and in the digital one it is false. Okay, then next thing we are going to see is that output. There are three kind of output that can be generated from this module. Okay, what are the three kind of output? That is, first is BA, that is nothing but a numerator by denominator form, or you may call it is in the form of transfer function, right? Then next one is ZPK, this one ZPK, right? The ZPK is a pole zero constant. Okay, or SOS, it is very much important in case of IIR filter, that is second order section. Okay, what is second order section? We have to learn first that, then we will go or we can enter this section, output section, more deeper, right? So for that, what is second order section? So here I search in internet, and to give you a visualization that while you are realize a IIR filter, there are in that realization you will get this type of block. Okay, these are nothing but the cascaded second order section. This is one section, this is one section, this is one section, right? These are all cascaded. You may hear IR direct form structure. The IR cascaded second order sections from structure have more computational complexity. However, the cascaded structure have, okay, there is no such information, but this is the thing. Second order uh, structure, right? Second order section means this type of section, right? So we are going to use this, because see, this is in Z domain. Means what? It is a digit. When we use generally Z domain in digital form, right? In digital domain we use Z form. So as we are here designing a digital IR filter, we are taking the output as SOS. Nothing means, this is a simple explanation for why I am taking SOS as output. Okay, so here, but I don't need any kind of means by default, what you can see, by default it is B by A. You can see from here Default is BA, right? That is the numerator by denominator. So I will get BA here. Okay, the B value and A value, which I am again going to take as input for next. I will explain that. Okay, so what it will return? BA, numerator and denominator it will return. Then the zero pole and system gain it will return, and SOS. It is a second order section representation of the IR filter. Okay, I think it is clear to all of you that all the parameter that we are used in this code, I just decode that from the SciPy library. Okay, so here the order of the filter is 3. My cutoff frequency, or here it is written as what, my critical frequency, right? Critical frequency. So my critical frequency is 1000. Then beta is low pass. By default it is low pass. Okay, analog is true, so it will generate a analog Butterworth filter, right? Okay, so similar to that, this also happened. The only change that it is present in this code, this line, is I just divide this critical frequency by fs, and it is if people have know this thing, why I divide this by fs. In the FIR filter designing I already mentioned these things. Okay, so I am not mentioning that again. And the next is here I make analog as if false, right? Because I am designing a digital Butterworth filter here, right? Then next the output is SOS. Okay, I already mentioned the reason for that, because we are dealing with digital domain, so we are going to take this SOS, and I tell the reason for that also. Okay, so this line and this line is get over. So let me comment this, generate Butterworth filter. Okay, next the freaks and SOS freaks. So for that, let me search here, that is freaks. Yeah, so what is freaks? You can see that. First one is BAWRN plot none. Okay, compute frequency response of a analog filter. Be careful. The only difference in analog and digital here is, in case of analog it is freaks S. Okay, S domain, right? You can, if you are forgetting, then you can remember like this also. And we already studied about freaks, FREQZ, that is in the digital domain, right? So this is the numerator and this is my denominator. We already generated these things, so we have to input this to this command, right? And this is a optional. If not, then it's compute 200 frequencies around the interesting part of the response part. Okay, by pole 0 occasion. If the single integer, then compute that many frequencies. Otherwise, compute the response of a angular frequency. Okay, so I think it is clear. It will return what? W and H. One is angular frequency, okay, and the H is my frequency response, right? Okay, so we used here this code, so we will get angular frequency and frequency response. So this the code, and I used 1024. I should mention WRN, right? Because I didn't mention that. Okay, by default it will take third parameter is uh, the number of frequency, right? Compute 2200 frequency by default, but I am taken 1200. Oh, sorry, 1024, right? So this command is for the frequency response. To calculate, okay, then it is well known. I just convert that into dB, right? So let me take to this code, this line, right? SOS flicked. So let me search that. So this is for the SOS flicked. What it will do? Compute the frequency response of a digital filter in SOS format, means second order section format. Okay, but the parameters first is SOS. We already calculated here. We have the SOS, right? It will output the SOS because I mentioned the SOS here. Don't think this is, if I write SOS here it will generate SOS. No, this is the variable name. Okay, the output name that you are mentioning here, that will return to that variable. If I write here ZPK, it will return whole zero and constant value to this. Okay, if I write BA, then it will return BA. Okay, so let's see once again. SOS array of second order filter coefficient must have shape. Okay, so these are all the things that we actually, let's go through this. Okay, I'm not going very much depth into that this. Okay, because I think you people have understood the thing. This is the WRN value, right? This is the number of frequency component it will going to calculate, and it will give a output as what? Let me see. The frequency at which H was computed in the same unit as Fs. By default, W is normalized to a range of 0 to pi. Okay, okay. So here I have to make a change, not max of W. It is divided by pi because it is, okay, yeah, because it is by default it is taking from 0 to pi. Okay, then H is the frequency response as a complex number. Okay, so these two things it will going to. So let me this also comment this frequency response. We'll also going to find out the frequency response in the digital domain. Okay, now this also clear to you. Nothing, we just do this due to the we want to convert this into decibel, right? Now the most important thing and a new concept of plotting that I have used here, I'm going to explain that. Okay, so here what I did was I mentioned a variable name and I given this variable name to my figure 1. Okay, the first line is that. Then the second line, what I did was I declared another variable fg and add a subplot there. Okay, because I want to plot multiple graph, you may say, in a single plot. That's the only reason I have to use subplot. Okay, so I just add a subplot there. Then I use semilog to plot this frequency response. Okay, then next thing, I just what I am doing here is I am taking that variable length fz, because I am doing the I am giving this subplot to the variable fg, right? So the title or plotting that I am going to do here, I have to do in fg. That's why I am using here fg dot semilog x, my two variable x comma y. X is my w, which that is the frequency, and h is my hdb is my amplitude, right? So I just mention that thing. Then I'm putting grid here, and for grid you can search it. If you have any doubt with which and axis, you just type uh, plt.grid in Python. It will show you the matplotlib library details. Go through that, you will get it. It is not that much difficult, so I'm not explaining that to you. You just do that, and if you find any difficulty, let me know. I will clarify your doubt. Okay, so the next thing is the plotting of the digital filter, that is here. So up to this much we have understood, right? So for the second one, what I did here is I just generate figure 2 and give it to a another variable fig2. Okay, then I use clf function. What is clf? CLF is similar to clear all in MATLAB. What clear all do in MATLAB? It will clear all the um, figure, etc., which are there in the command prompt. Similar to that, what CLF do in Python is that it will clear the figure that is actually generated earlier. Okay, and why I did this? Because I want to plot another figure in that. Okay, so I did the same thing, same step here. I just add another variable, just give to that variable subplot of that to the variable, and I just use the properties. Here I am using plot because it is in normalized range 0 to 1, so I am not cutting this with respect to frequency. Okay, and if you have any doubt why I didn't use Semilog in my previous videos, you can go through that, because I from in that video I first figure is normalized one, then the next one is where I used a frequency in hertz in the x-axis, and then amplitude. In that case also I may use you can use a semilog graph, but for the sake of simplicity, for the better understanding, I use its normal plot there. But in this lab, as I already told you about that thing, I just add this in a semilog graph. And usually frequency response, or you may you can in the BTech level you have seen about Bode plot. These are all done in Nyquist plot, Bode plot, not Nyquist plot exactly. Bode plot is generally done in our semilog graph, right? So that is nothing but the frequency response. So many of the frequency response are uh, like Bode plot. These are done on semilog graph. So here I want to show you that how to plot that semilog in Python. That's the main reason where I use cellular here and plot there to uh, get your clear picture, right? So I think it is clear to all of you. So let me run it once again because I change here. I make a changes that is w by pi. So let me run it once again. So, yeah, so you can check it. One thing I can do to know where is the cutoff. So let me add a new thing here, that is elp dot axb line, vertical line at it is, we are taking its 1000, right? 1000 comma 1 is equal to, suppose red. Okay, so what it will do, let's see. Yeah, that's the thing. At 1000 hertz it will generate a line, vertical line. You can see it. Okay, so at 1000 hertz my frequency response decay. Okay, so for the mm, sake of simplicity, or you may for visualization, I just draw this B line. It is optional, you may draw or you may not draw. Okay, so okay, now let's see, if we increase the order of the filter, what will be the response. So let me do that. So let me change it to 7. Okay, 7, and this also to 7. Okay, yeah, and other thing remains unchanged. Okay, yeah, can check. Can you guess the change? What are the changes? Yeah, I am unable to actually get it. Okay, let me undo this. Okay, let me run it. Yeah, here it is little bit stiffer. Okay, if I change this, let me change the theme. Yeah, so here is 7, and here also 7. Okay, so here, and we change. Yeah, here is the major change that you can find. Okay, so I think it is clear to all of you that how to create this and what are the module that I have used here. I clearly explained that thing. So anything you are not able to get, just Google it, and still if you have any doubt, then I will clarify your doubt. So first try by yourself. Then if you still not getting any solution, let me know. Then I will try my best to uh, get your doubt clear. Okay, so this is about Butterworth IR filter, uh, IR Butterworth low pass filter. Yeah, this is okay. So let me undo this. I have to make uniformity. So Okay, so sorry. Okay, so now in our next cell, now let's write a code for uh, our Butterworth high pass filter. Okay, so there are no major change that are there in high pass filter designing. It is pretty similar to low pass filter as we see in FIR filter, right? So in FIR filter we see that the low pass filter designing and high pass uh, filter designing, there are not uh, much changes in that. The code are pretty similar, right? So here also in IR filter also we uh, cannot we are not uh, have any major changes that are there in high pass filter designing as compared to the low pass filter. Okay, so for that reason, let me do one thing. Let me take the code from here and make the requisite changes that is needed, and let me run that for the high pass filter. Okay, so let me paste it here. Okay, so I just paste it. So let me change the required thing. Here it is high pass filter, then this also high pass filter. Okay, here we have to make it as a high pass filter. Okay, yes, then high pass filter. Okay, then here high pass filter, right? Here also make it as a high pass filter. Okay, here also same thing. Yeah, no other thing I need to change, right? There are similar only. Now let's see the output for this. Can you see this? This is the output of a high pass filter. Okay, if you have any problem in this axis, you can minimize that also. There is no such issue with axis option. Okay, if you don't know, let me do that for you. How to add axis to that? It is similar to that. Or I can use plt.axis also. It is better. Okay, let me start with 0 and end with, for x-axis, end with 10 to the power 5. It is 4. So let me run it. Yeah, some error. Yeah, it is actually axis. Let me run it. No, there are other thing. So okay, I'm getting error, so let me use fg.access then. Yeah, it will work. No. Yeah, x minimum, x max. Maybe it is not taking that. 0. Maybe there is some. So make it to 1. Oh, it will take the other parameter also. So let me do for this also. Y is 0 to minus 100,000. No, got it. So here is the wrong thing that I have did here. This is x mean 0. From 10 it will better. Still I'm not getting the answer. It's not 0. This must be 1 maybe. Still not getting. Okay, skip this. I am not able to actually now do this because this is the but this is the way in which we can put the limit to x-axis and y-axis based on your required output. Okay, so in this way we can put the thing. So but I now what I'm not able to get the thing, so for this I need maybe take time, so let me skip this. Okay, so you can please don't add this because it is better. It's working right. So okay, this is about the high pass filter designing. The next thing that we are going to do here is for the designing of band uh, band pass filter first, then we will see band reject filter, or you may say IIR, Butterworth band pass filter designing. Now we are going to see that this thing. Okay, so let me start the coding. So here we need totally different thing. So what I will do here is that I will write the code for the generation part, but for the plotting part it is pretty similar. So I will do I will take it from the above code and I will just do the thing. Okay, so let me write the code what I have did here. Okay, so code for the designing of IIR Butterworth IIR Butterworth band pass filter. Okay, PPA, right? So for this, similar to the this code, let me write for analog IIR band pass filter, similar to that, p comma a is equal to better than 3. Here, as I told you earlier, that in case of I already show you that module, right? That butter module from SciPy lab, SciPy, that in uh, the second parameter that is there in this module, we can supply a frequency or range of frequency. So as I told you earlier, here we have to give a range of frequency here. So I'm going to give 100 comma, because I already mentioned 1000, right? Yes. Then B type, right? My B type is band pass. Then analog. Yes, it's analog, right? Yeah, analog is equal to 3. It's not true. Okay. So this will generate the IIR or Butterworth filter. Okay. The next is W comma H, which is equal to freaks B comma A 1024, or you may mention WORN, which is equal to this. Okay. So what it will do, it will generate the frequency. Okay, it will generate the frequency response. Okay. Now the next code that we are going to do here is pretty similar here. So let me take this to here and paste this and make the required changes that I have to do here. Okay, so for the flooding, yes, so here I have to make it is as a band pass filter. Yes. Okay, then here other thing that I have to add here is this, because there are two cutoff frequency, I have added a vertical line there. So let me add another line at 10 also, not 10, what is my 100, right? So let me add another line 100. It is in the red also. Okay. Okay, this is about for the this is for the analog air filter. Now let's do for the for digital IIR band pass filter. Okay, now here what I have to do here is we have to find SOS, right? We already know why we are finding SOS. Better 3 comma. Okay, so 100 divided by fs comma 1000 divided by fs. Okay, and the reason you know. Then b type is equal to band pass, right? Then analog is equal to false. Then output is equal to, sorry, no, this is SOS. Okay, then another parameter I am directly adding here, fs is equal to what the sample frequency I have taken, 10 to the power 4, right? So I am taking 10 to the power 4. Here also I can give directly fs here. Okay, because this uh, attribute also contain a parameter that is called fs, that is sampling frequency. So I can write it here to show that I am using this like this here. Okay, to get you a uh, get you this idea. Okay, okay. So now next code is w comma h, which is equal to what is SOS freq freq right? Yeah, is equal to next SOS comma, let me see this. Okay, so WORN is equal to 1024. Okay, then rest of the thing are similar. So let me take this it from here. Okay, so just copy it and just paste it here. Yeah, so what are the changes that I have to make here is it is a IIR band pass filter. Okay, no other thing I have to no okay, this is the changes that I have to make, other are same only. Okay, so I can add it here, the comment generate filter. Okay, what it will do, it will generate frequency response. Okay, yeah, so this is all about the coding. Now let me run this file, now this code. you can see that in this range from 10 to the power 2 to 10 to the power 3 there is a passband, there is a output. Okay, and for other values there are negative amplitude, you may say, in dB. Okay, because these are all in dB. Okay, so I think it is clear, and this is in the normalized frequency range. Okay, okay, so this is all about the uh, band pass filter, right? We are designing band pass filter, or IIR Butterworth band pass filter. So let me change the length and see the effect. So let me change it to 7, and here also change it to 7. The normalized frequency amplitude response digital, it's little bit weird, it is actually coming, but the analog one is good, right? But in case of this we are getting a right thing, but why we are getting this type of output here? Okay, it's maybe due to the different parameters that we are setting. Okay, so with 7 we are getting this, right? So let me do one change to see the effect. Yeah, it's coming same only, right? There are no any changes. Okay, so you can use max W also, right? Because the plot that we are actually getting from by writing by dividing with it by pi, or by dividing with max of W, it's same only, so you can use this also. Okay, so this is all about our band pass filter. We already seen the high pass filter and the low pass filter in the previous two cell, right? So now our next task is to design the band stop filter. Okay, so for that, now let's start. So let me take the code from the above cell. Sorry, just paste it here and make the few changes. Band stop filter BSF. Okay, here also band stop filter. Then let's start with first three. Okay, here it is going to be changed as band stop. Okay, Yeah, then here bend stop. Okay, now let's go to the digital one. Bend stop. Okay, then here also bend stop filter. Okay, sorry, I just mistakenly delete that. Okay, so now it will be right. So let me check it once again. Okay, here it is small s, not small s. It's capital S, right? Yeah. Other parameters are same. So here also it is capital S. Okay. Yeah. So now let's run this to see the output. Here you can check it that in between the range of 10 to the power 2 to 10 to the power 3 there is no frequency. These are the slope actually that is present over there. So we can check it by increasing the order. What happened? We are not getting in the output domain, in digital domain, right? We make some wrong somewhere maybe. So let me, yeah, actually I made a mistake here in the previous program, that is in band pass filter. So I want to make the change that I actually that I have done. Okay, so here you can give 10,000. So let me check it whether it's giving the output or not. It's pretty weird actually. So it's better to take twice of that. It will be better. Okay. So that let me make change. Then I will explain what I actually did. So for sampling frequency, take it as 2000. Output visualization, nothing else. Okay, so you can check it here that the changes that I have made in uh, this I already told you that I in that previous code I mentioned fs here, but now I am mentioning fs here because it will give some other type of output here. That's why I am mentioning from the earlier of this line, okay, such that fs can be defined, right? So I just define this, then I used the same thing, then I am executing my code. So let me do that once again. You can see the output now. Okay, it is due to the normalization, it is little bit weird, but till now it is showing as a at least like a band pass filter. Okay, so that's the thing, that's the change that I am make here, and other are same only. the same change, let me do it here also, so that I will get the output. Fs is equal to 2000, let me take it and make this as a 3. Okay, you will already make this as a 3. Okay, now I can run this to see the output. Yeah, you can see that it's pretty much similar. Okay, so this is the uh, I think we cover all the thing for the design of Butterworth filter, IIR but filter designing. Okay, so I think all, let me take it once again from the below code, from the starting. So here we take the all library that we did, then we write the code for go past filter. Okay, and in this I explain all the thing, all the attribute, all the library modules that I have actually used in this lab, and I go bit by bit, line by line of the program, and tell you how I actually write the code and what are the parameters for the modules, and how actually it is, how actually you can alter this parameter to get different kind of outputs, right? Then I explain you about the plotting method that I have opted here in this video, right? So this is a little bit new one for all of us, all of you, right? I already know. Okay, so this is new to all of you. So I just give you a new idea here. Then next we design the first we design the analog filter, then the digital one. After that we see the output. Then next we design the high pass filter. Then we design the high pass filter, and we see its output and other thing, right? Let me take it to the down. This is the output for the high pass filter. Okay, both for in digital and analog domain we have seen, right? We are using here semi-log graph to plot the amplitude response of the filter, right? And for plotting the digital frequency response we used normal one, right? So this is for the band pass filter, and this is for band stop filter. Change it to this. Okay, I think all of you uh, get it, to how to write the code for uh, designing of IIR filter. So in our next lab we are going to see the next part of this, that is designing of IIR filter, IIR Chebyshev filter, in which we are going to design both Chebyshev 1 type and Chebyshev 2 type uh, IIR filter. Okay, and we see some basic theory behind the Chebyshev filter also. Then and as we don't have sufficient time today, because I have to wind up the thing within 2 hours, so for that reason I am not starting that new topic. I will start that one in the next lab. Okay, in lab 12 we will see that, and we will finish our IR filter design, Okay, so this is all for today's class. So thank you.